It's a great pleasure to be here. I looked at my files and I realized that the last time that I'd been on campus to talk research was 2011. I'm thrilled to see the changes that are going on, especially perch. I'd like to move in if you can find room for me. And I was thinking about what to present here today at Penn. And first I thought about some of the more analytical work that I'm doing with my students for state estimation and navigation. And proving some theorems. And then I thought about Dan and George and Kostas, and I said, the students get a lot of that. So I thought that instead I would tell you a little bit about the most recent field work that my students and I have done in collaboration with the Woods Hole Oceanographic Institution. Tell you a little bit about developing and deploying underwater robots for oceanographic exploration. So this is essentially going to be the field report for the first two deployments of an underwater vehicle that my collaborators and I developed over the course of the last 6 years, primarily with development funding from Office of Polar Programs of the National Science Foundation and with fieldwork funding from NOAA and NASA. So just a little bit of background. I work on dynamics, navigation, and control problems, and I'm happiest when I can find a problem that actually might solve a problem in the field that has an interesting theoretical question buried in the problem. It doesn't happen all the time, but that's the kind of thing you look for, like shiny gold coins. And right now, my research is primarily focused on navigation and control of underwater vehicles for oceanographic applications, and also teleoperation for on-orbit servicing of satellites. The things that I was originally thinking about talking about, which do have some good math and system theory. I'll just name them. I won't go into any of the details. I've got a couple of students who are working on what we call cooperative navigation. And the idea is that when you have underwater vehicles in the water, it's a GPS-denied environment, and there is no RF communication between the vehicles. Unless the vehicles have a tether to them, which limits their mobility, the only communication channel that you have is through the water column, which is a time-delayed communication channel. Sound travels about 1.5 kilometers per second in the water column. And the bandwidth is very low. And so our vehicles typically transmit a 64-byte data packet a couple times a minute at most. So that's it. And at those data rates, you can have communications out to a couple of kilometers. If you want longer ranges, then you're going to have to drop the data rate considerably. So the thing that my current and former students have been working on is if you have acoustic modems that have atomic clocks built into them so that they know time to sub-millisecond accuracy over a period of many days, then every time one modem does a transmission, it can encode what it thinks its state is. And all the nodes that receive that data transmission can timestamp its reception. And if you know the sound velocity profile in the water column, you can generate a range. So by doing this, we can navigate multiple underwater vehicles and simultaneously navigate and communicate to multiple underwater vehicles. So my current students working in this area are Zach Harris and Laughlin Barker. Another project that right now is actually have funded from NSF Ocean Sciences is to develop both theory and hardware for low-cost north-seeking gyros. Knowing where north is and where down is very important in navigation. In fact, it's the most important thing in navigation. And for the types of maps that we would like to generate maps that are sub-meter accurate over kilometers of scale. And so you can't do that with magnetic compasses and crappy roll and pitch sensors. So this project, which is sponsored, it's an NSF grant that I have from Ocean Sciences, is to develop a low-cost theory and hardware for low-cost north-seeking fiber optic gyros. The IMUs that I'm used to using cost $150,000. They are this big. They burn 20 watts, and they weigh about 7 kilograms. And so that's not an IMU you're going to put on a small low-cost vehicle whose total cost is maybe $50,000 or $75,000 and has a hull diameter of 10 centimeters. Just not going to happen. So in this project, and there's a upcoming ICRA paper on this, We've worked with a company called KVH, which many of you may know, and you may not know that they have a 1750 fiber optic gyro, which goes for only $20,000. It's a couple of kilograms, and it draws less than 5 watts. And the optical, it has also got 3 MEMS accelerometers. And so with Andrew Spielvogel and help from undergraduate Emily Palmer, we've been looking at adaptive estimation on SO3. And so the signals you have to work with are the angular rate outputs of the gyro and the accelerometer. And if you can compensate the bias in the gyros in the accelerometers so that you can have a stable frame of reference with respect to the stars that is stable on the order of 0.5 degree per hour, then you can find north using that. And to compare it, because when you want to compare it, Earth rate is 15 degrees per hour. So you need to have a stable reference with respect to the stars that's substantially, the noise level is substantially below Earth rate.
Which stars are you referring to?
The fixed stars. I'm talking about an inertial reference system that's not rotating with respect to the fixed stars. And so we don't have one of those. It's not easy to instrument one, but we can measure angular rate. And it turns out that the really hard problem here is two things. You want to do stable estimation on SO3, and the confounding factor is that you have biases in your angular rate gyros and your accelerometers, and you need to figure out what those biases are while the vehicle is moving. You can't set down and do sort of like benchtop bias compensation. So enough about what I'm not going to talk about. The project that I am going to talk about is one that I've been working on for 6 years with my collaborators at Woods Hole. The PIs in the project were Andy Bowen, James Kinsey, Danny Yorger, and myself, and Chris German. Chris German is a geologist. Larry Mayer is a hydrographer from the University of New Hampshire, and the rest of us are engineers. And we had just finished around 2010, 2011, we had just finished the development of an 11,000 meter capable vehicle, the only one in the world. And in fact, that's the subject of my talk last time I was here. And we knew that the technology that we had developed for that vehicle would be useful for developing an under-ice vehicle. So we wrote a proposal, an MRI proposal. Oh, I want to brag a little bit about my collaborators. My collaborators in this story are with the Deep Submergence Lab at the Woods Hole Oceanographic Institution. And think of Woods Hole Oceanographic Institution, or WHOI, as a graduate school for ocean sciences and engineering with no undergraduate program. It's a private institution located in Massachusetts. It's got 6 departments and about $160 million in externally sponsored research. And I'm an adjunct in the Applied Ocean Physics and Engineering Department. I think I'm going to skip over this slide. The ocean is really deep. The average depth is 3,700 meters. And it's almost completely unexplored by humans. We know more about the surface of the moon than we know about the seafloor. And over the last 20 years, it's been a pleasure to collaborate with Woods Hole to develop navigation and control systems for a number of the Woods Hole vehicles, some of which you may have heard of. You've probably heard of Alvin. And you may have heard of Nereid, which was the 11,000 meter vehicle, which we lost, unfortunately, in spring of 2014 on its 76th dive. It was doing science at 10,500 meters in the Kermadec Trench in the Pacific, and one of the ceramic pressure housings imploded and killed the vehicle. And we're just now starting a project to develop the next generation Nereids, so we're engaged in that right now. The thing that we started looking at about 6-7 years ago was an idea that had been around for a while, which is that the technology that we developed for Nereid would enable us to develop an underwater vehicle that could operate under fixed or moving ice. The motivation for that is while 71% of the Earth's surface is covered with ocean, 12% of the Earth's surface of the oceans are covered with ice for some or all of the year. And on this motivating slide, you can see the Arctic Basin right here. This is the Gackle Ridge. This is the Lomonosov Ridge. The Gackle Ridge is one of the slowest spreading centers. It's a mid-ocean ridge, one of the slowest spreading centers in the world. Been almost completely unexplored because it's covered with ice most of the year. And we know from Hetty Edmonds' cruise back in 2002, her Nature paper indicated they took water samples along the entire length of the ridge and they found abundant signs of hydrothermal venting all along the ridge. So we know that there are active volcano systems along the entire length of the ridge. Nobody's actually ever seen and sampled one. And so the limitations with conventional tethered vehicle technology is that the tethers that we use to go from the surface to the seafloor are big, heavy steel tethers. They hang more or less vertically, and when you have a wire over the side in the ice, and unless the ice is vanishingly thin, you're not going to be breaking ice. And so you lower the vehicle down here with a weight on the end of the tether, then you have a neutrally buoyant tether to this vehicle, which can drive around in a very small radius of the vertical steel armored cable. Meanwhile, you have moving sea ice, and so the ship is being carried off downrange by the wind-driven moving ice at between, say, a quarter knot and a knot and a half, depending on the conditions. And so you can't control the ground track of the vehicle, and you can't just say, go over here to take a look at this interesting feature that you've seen in the multi-beam map, because your tether won't let you. And the thing that we developed for the 11,000 meter vehicle was a very lightweight tether, neutrally buoyant in the water column, carries data but no power. And here's a sample of it. It's a piece of optical fiber, 125 micron diameter glass core with a 250 micron diameter buffer on the outside. Carries HD video and as many gigabit Ethernet channels as you care to have. It's a little bit thicker in diameter than human hair. And the design concept for this vehicle is as follows. You lower a depressor from the ship through the ice, and at the bottom of this depressor, there is a canister which carries 20 kilometers of fiber spooled up very tightly. The canister is about this big. The fiber is really thin, so you can fit a lot of fiber into a small canister. And the vehicle has a tow body that it tows, and inside that tow body, it's typically about 20 meters long, this distance here. There's another 20 kilometers of fiber spooled. And this whole assembly goes over the side with this tow body docked into the depressor. You lower down to the depth of operation and then release the tow body. And then the vehicle can freely drive both horizontally and vertically, and the ship can be carried off downrange by the moving sea ice. Reasonable question, what happens when the tether breaks? So we expect the tether is going to break in most dives at some point during the dive, or if not, it'll break during the recovery operation. And so we have acoustic communications to the vehicle, and when the tether breaks either deliberately or unintentionally, then we end the dive and we command the vehicle to head back to the ship, and we give it a series of moves to navigate around the bow of the ship, come up on the starboard side where we've created a small opening in the ice and a surface in the ice, and we can do that acoustically. This vehicle is also capable of doing autonomous operations where there's no tether. We strip off the robot arms and other accoutrements, and it can be used for survey operations. And in that configuration, it's much more streamlined, and we can give it a pre-programmed survey to run, and we can also send commands to interrupt that survey if we want to preempt it to do something. So that's the idea for Nereid Under-Ice is the name of the vehicle, and our German collaborators quickly abbreviated that to NUI, and so that's the name. And the operational concept of this vehicle that we pitched to NSF is that if we have this idea of having 20 kilometers spooling out here, 20 kilometers spooling out here, ship gets carried off downrange any number of kilometers. When it's time to recover the vehicle, you put the vehicle in auto XY on the seafloor, basically park it, pull this thing up through the ice, break ice back to the top of the ship, lower the depressor in, get acoustic comms to the vehicle, command the vehicle up to the ice, and then incrementally drive it over via acoustic commands to the starboard side of the ship where you've got a small opening and surface it. Sounds easy, right? Turns out it actually works. There's a second use case which is really important to scientists, which is that of exploring under ice shelves. And an ice shelf is, there's fixed ice, which is ice that's frozen and attached to land, but an ice shelf is a different creature. It's when a glacier slides down out of a mountain, hits the ocean, starts melting from the bottom, and ice shelves are typically 50, 100, 200 meters thick. They're floating, so they're a giant structure, and the undersides of very large ice shelves like the Ross Ice Shelf, the Pine Island Glacier down in Antarctica are almost completely unexplored. We know there's life under there, but we don't know much else. And there's one group that's done really, really good work at mapping out under ice shelves. The University of Southampton have a vehicle they've developed called AutoSub. We're now at AutoSub 3. And it's a torpedo-shaped vehicle. It's about 1 meter in diameter. It's about 7 meters long. It can't hover. It has to fly forward. And it has upward and downward-looking multi-beam sonars. And so it's perfect for doing surveys and physical oceanographic surveys under ice shelves. A superior vehicle for that. However, it can't hover. It can't sample. Has no cameras. And doesn't have any ability to do any close-in observation. So we wanted to fill in that sort of middle ground of direct human intervention with this vehicle by use of a light fiber tether. So the vehicle we developed, as I said, is called Nereid Under-Ice, or NUI. Those are its specs. Just a quick numbers, it's got a depth rating in its current configuration of about 2,000 meters. Carries power in 18 kilowatt hours of lithium-ion batteries on board, pressure tolerant. It's got upward and downward looking acoustic Doppler current profilers, upward and downward looking multi-beam sonar, and a whole bunch of physical oceanographic sensors for measuring conductivity, temperature, depth, oxygen, fluorimeters, and on the 2014 expedition, we had a bunch of light sensors because we were operating in the upper water column in the top 50 meters. And so with the ice physicists who were the scientists that we were working with, we were measuring light transmission through the ice. Our first opportunity when we wrote the proposal, we had contacted a biologist at Alfred Wegener Institute in Bremerhaven. Her name is Antje Boetis. And she had a cruise scheduled 4 years ahead of time from when we were writing the proposal. And she wrote us a letter that said, if you build this, then I'll find a place for you on my cruise. And so we built it, and we called up Antje and said, Antje, we built the vehicle, it's almost finished. Can we come on the cruise? And she said yes. And we said, by the way, we've run out of money, but we're gonna try to get some more. And so we did get some money from NOAA. And we went on an expedition on the Polarstern. Antje Boetis was the chief scientist. This is a ship that weighs 18,000 tons, carries an officer and crew complement of 50, and a science party of 50. And it spends its summers in the Arctic and its winters in the Antarctic. This was our engineering team in 2014, including software engineer, my postdoc, Christopher McFarland, electrical engineer, Mike Jakuba was my former postdoc, who's the expedition leader, me, and a technician. And our goal was to go up to 83 north, 6 west, which is about 200 kilometers northeast of Greenland. So this is just the top end of Norway. Finland is over here. This is Greenland, and this is Svalbard. Iceland is down here someplace, so Iceland is pretty far south. So we mobilized in Tromsø, Norway, which is just above the Arctic Circle, and we transited, leaving Svalbard to the starboard, up past Greenland to this side on the Gackle Ridge. And you can see this is the Gackle Ridge coming down through the Fram Strait. It eventually comes down here and comes on dry land in Iceland. And Iceland is right on the Mid-Atlantic Ridge. And we spent a little over 2 weeks right here at this site, which is on the southern part of the Gackle Ridge, where there was strong indications of hydrothermal venting. Our vehicle operations were all in the upper water column there because the seafloor was at 4,000 meters, so we couldn't dive to it, or if we dove to it, at least we wouldn't come back. This is prepping the vehicle for a dive, and this particular dive was in tethered mode, but we were not doing we didn't have the robot arm on it, and you can see there's 2 pumped CTDs that have a bunch of sensors on them for measuring properties of the water column. We're doing a vertical and horizontal transects. This is an HD imager inside of a dome. And this gives you sort of a sense of the scale of the vehicle in comparison to your average German crew member. The officers and crew of the Polarstern were really, really wonderful to work with, and they are totally expert at putting highly unnatural things in and out of the ocean. And so they were a real pleasure to work with. This gives you sort of a sense of the vehicle. We were in a laboratory on the main deck level when we were working on the vehicle in sort of nice conditions, warm conditions. This is the launch and recovery launch system that we had in 2014. We did a single pick launch. This is the depressor, this is the tow body. Everything's mated together, it goes down here. The launch sequences, we lower it down to 50 meters, which is 40 meters below the bottom of the ship where the propellers are spinning all the time. Do a vehicle checkout. If everything checks out, we release the tow body from the depressor and the vehicle drives away. Recovery is a little bit different than deployment in that we were typically navigating acoustically, commanding the vehicle acoustically into an open water pool on the starboard side. And when our instruments told us that we had navigated to the starboard side and there was open water above, would surface and then command the vehicle over to the ship via RF modem. This is the vehicle on dive number 2, I think, driving away from the ship. Mission control in a laboratory on the ship. And this gives you a sense of, this is a dive track, and the actual dive track was back and forth, left and right. But basically, what you want to do with this, since you're paying a tether out behind the vehicle, you don't want to eat your tether. So we dropped down to about 43 meters, and then we headed downstream with the prevailing current as the ship was rafted in the ice, and then came up, turned around, and this is dive track. This is distance along track, and this is depth from sea level here. Sorry. So went downstream till we were about 1 kilometer away from the ship, came up, turning around, and then started heading back towards the ship in a series of transects, moving upstream so that our tether would be carried downstream and we wouldn't run into it and eat it with our propellers, which is one of our engineers referred to it as propeller flossing. And so this is where we're doing a series of transects. The upward-looking sonar is measuring the depth of the ice, and so these are ice keels where the ice is, there's an ice keel of 10 meters, and here's an ice keel of 7 meters, and you can see the average thickness of the ice is a couple of meters. And we did we'd go in here and go put the vehicle on auto XY, and then do a very slow vertical transect while pumping water through the CTDs and all the instruments, getting vertical. The main folks that were interested in that were our plankton biologists who were interested in plankton distribution in the upper 50 meters of the water column. This is in July, so it's the Plankton Bloom. The plankton is the primary means of biological production in the Arctic. Everything lives off of it, directly or indirectly. And we're just learning about the amount of biomass it creates. Came up here, we sat the vehicle under the ice and took a look around for a little while. And then on these are horizontal transects where we're driving at 2 different depths. And we have upward-looking irradiance and irradiance sensors. And the ice physicists that we were working with had the exact same sensors, and they were trudging around in the ice, carrying them around, measuring the incident light, and we could measure the transmitted light. This was an algae map that Antje was quite interested in. This shows, this was dive number 4, and you can just sort of see the idea here is we head downstream fast, and then went along a transect here. And on this survey right here, actually, the ice physicists had drilled holes in the ice and put poles through them, and we flew right along the line of poles, and they measured the incident light while we measured the transmitted light. This is a vertical transect showing chlorophyll distribution, salinity, temperature, and you can see the vehicle this is a depth rate versus depth, and so we can very precisely control the vehicle vertical movement while it's locked in auto XY using an upward-looking Doppler sonar, so locked to the ice via closed-loop control. This is the first journal publication that came out of that cruise, which was the influence of ice thickness on light transmission through the ice in JGR, Journal of Geophysical Research. And I thought I'd show you a video. Give me a second. So this is dive number 3 from 2014. So we're looking at the vehicle's HD imager. It's looking perpendicular to the ship on the starboard side, away from the ship, and you can see the ice looks kind of smooth. This is multi-year ice, meaning that it has been frozen in a previous season, probably broken up and then refrozen. And from the ship, we went down to 50 meters and drove away from the ship to get away from the moving propellers. The ship has very large propellers that are about 7 meters in diameter, and they rotate constantly, variable pitch props, and it would be bad to be sucked into them, so we stay away from them. And this is looking upward from Nui with the HD imager, and here you can see on the underside of the ice that it's clearly multi-year ice. It's an aggregate. It's not smooth. It's not just like a smooth piece of lake ice. It's clearly been broken up and refrozen. And the snot that you see in the water column is zooplankton, mostly larvaceans, that are feeding off the phytoplankton, which is the primary means of production. And I don't want to run out of time here. You can see that in the shallow, in the places where the ice is thin, there are algae mats that form. And the reason that this was a big deal for our physical oceanographers and our ice physicists is that when you have an 18,000-ton ship, which has propellers that's turning all the time and lateral thrusters that are turning all the time, basically you're mixing up the upper water column pretty substantially with a massive amount of horsepower. And so you can't just lower something off the side of the ship and make an undisturbed measurement in the water column. You need to send people out over the ice, drill a hole in the ice, put things down. Or you can deploy a vehicle like this and have substantial mobility. So this is where we had the vehicle ballasted to be about 3 kilograms positive, and so when we stop thrusting, we could just rise up under the ice, and there's little legs on top of the vehicle that could sit on the ice and look around for our biologists and the ice physicists. This is looking forward with the HD imager, and these things are about 2 centimeters long. They're called larvaceans. They're not unique to the Arctic. You find them all over the world. So they're a zooplankton. They move at really low Reynolds numbers, like 10. The little flagella that you see is not actually for propulsion. It's to stir the water to bring the zooplankton to the outside of the larvaceans. They have no mouth, and so they stir the phytoplankton into the gelatinous exterior of the larvaceans, and they consume them there. That's their mouth all over their body. This dive 3, the tether stayed intact all the way back to the surface, which doesn't always happen. We were really rookies at this on this cruise with this vehicle. It was literally dive 3 in the Arctic. And what you see there is the image of the ship's crane on the starboard side of the ship. And this is looking down on the vehicle. It's under RF control once it breaks the surface. So then we can just drive it over to the ship and scoop it up with the ship's crane. That's the depressor looking out. That's the butt cam in the vehicle. And that squeaky sound that you will hear occasionally is the acoustic modem. It's the 10 kilohertz acoustic modem. We have a 10 kilohertz and a 3 kilohertz system. That sound right there. So this was in July. It was lovely weather, occasional snow, not too many storms, lots of light, 24 hours a day. That's it.
What's the mass of this
About 2,000 kilograms in its current configuration. So, sorry about that noise there. So let me finish by doing a quick blast through a cruise that I just got back from. We got back to, we had another opportunity that we planned for, and we almost didn't make because we didn't get funded until about 5 months before the ship actually left the dock. The funding for this expeditionary work came from the NASA astrobiology program, where the idea was that we would look for indices of life on a part of the Gackel Ridge that is very shallow up at 87 North. There's a seamount at 87 North, 61 East, sort of north of Russia and Novaya Zemlya, about 180 miles from the pole, that rises to within 600 meters of the surface. And the geologists looked at there's been a little bit of multi-beam taken by this ship 5 years ago, not the entire top of the seamount, but our geologists, such as Chris Dermond, who was the PI on that NASA grant, looked at it and said, there are hydrothermal vents on the top of that seamount. Let's go find them. We'll be famous. We got funded at the very last minute, and it was a full sprint to get the vehicle ready. We had to go out and buy a robot arm to add to the vehicle and modify it for our purpose. In this cruise, we had 5 engineers and a science party of 3. So we were even thinner on the ground than the previous time. And on this cruise, we mobilized in Tromsø, Norway, which is right here. So here we can actually see Norway. There's Novaya Zemlya. So you can see the Sorry. You can see the Russia over here, and we're at 61 East. This is the North Pole. We mobilized in Tromsø again, one of my favorite towns in Norway, and we transited up here to just outside of the Russian zone, to the east of Svalbard, and met the ice right around here. This was late in the season. We left on September 9th, and we got into Bremerhaven, Germany, 45 days later. We were on station up here for about 27 days. And the sun came up for a little bit during the first week, and after that it was noontime was basically a little bit of twilight at first, and then towards the end of the cruise, noontime was just night. Then we transited back, breaking ice, to Svalbard, picked up some ice buoys here, and then transited all the way back to Bremerhaven. So this is the vehicle in its ROV configuration. The goal of this cruise was to do work on the seafloor, not in the upper water column. For Nereid, we had developed an electrohydraulic arm together with Craft Telerobotics, and we built a newer version of that with some improvements over the previous one. It's got an electric HPU, and it's a 6 degree of freedom electrohydraulic manipulator. And in this configuration for ROV operations, the sample basket is here. For AUV operations, this thing goes away, and we have a streamlined nose that fits on the front of the vehicle for autonomous operations. So these are some of the data from Nereid Dive 15. And so what's going on here is this is a 500 by 500 meter box where the vehicle was commanded to dive down to the bottom and do track lines in a 500 by 500 meter box at 50 meters off the bottom with a downward-looking multi-beam so we could make a sub-meter resolution map of the area. The ship has a multi-beam sonar, and so we can get sort of the general shape of the top of the seamount, but the resolution with the shipboard low-frequency multi-beam is on the order, at these depths, probably several tens of meters is the feature size, whereas we can resolve sub-meter. And then after doing this 500 by 500 meter box, went and did two very small photographic transit boxes with the vehicle terrain following at 3 meters off the seafloor with a stereo camera pair and a strobe. And sorry, what is the data? So X and Y is in latitude and longitude, but it's a 1-to-1 scale. There's temperature, microtemperature here, and you can see the scale here. EH is redox potential, which is an indication of fresh hydrothermal vent fluid. This is actually a very sad story because there's not much going on here in the EH sensor. And so the hypothesis that there was just hydrothermal vents all over the top of this mountain was not true. We didn't find one. But we did find something we didn't expect. Bottom depth and turbidity from the turbidity sensor. So we weren't heroes for finding hydrothermal vents. The mapping worked out beautifully. This is the data from that survey. This is actually the version that we processed on board the ship. I believe that one of my collaborators at Woods Hole has done some better post-processing that will clear up some of the image anomalies. Like, for example, that's not real geology right there. This is Casey Machado. She's the lead mechanical engineer on this vehicle, and she's also the pilot driving. This is the scene after dive 16, I think. The vehicle was configured in ROV mode. Here's the sample basket. This is a sponge that we sampled. This is a deep sea coral that we sampled. This is a happy myophonobiologist with a push core. And I've just got enough time to show one more video. So this is Nereid Dive 16. So this is just last fall. And the vehicle's, that's an AUV launch. You can see the vehicle has a streamlined nose on it. So this is an AUV dive, and there's always like a little feeling that you get in your stomach when you give the acoustic command. You're like, okay, dive, go for it. Hope we see you again sometime. And so we command the vehicle to drive down to the seafloor. It does that autonomously, and then once it obtains bottom lock on the seafloor, it switches to the downward-looking Doppler as its navigation source and the north-seeking gyro, of course, and does dead reckoning. We can provide corrections to the vehicle's position with one-way travel times using the acoustic modems. The vehicle is equipped with atomic clocks, so is the ship. And so we weren't heroes. We didn't find any hydrothermal vents, and we didn't get that cover story in Nature. But we did uncover a huge mystery that the biologists have yet to explain to us. What is a haddock doing at 86 North? Haddock shouldn't be there. It should be way far south, maybe in the Fram Strait, but it doesn't belong there. And when we got down to the seafloor for the first time, when we looked at the first images from the AUV dives, and when we got down to the seafloor for the first time in ROV mode, where we have HD video, this is what we saw. There was abundant life everywhere. These are sponges. There's sponges, starfish, deep sea coral, shrimp, all sorts of things in very high density. And the biologists expected this to be a desert because everything here, according to their theories, lives off the rain of dead phytoplankton and zooplankton that rain down only during the summer months. There's not much biological rain during the winter months because there's no sun. And so this is starfish feeding on a sponge. And so this is another example of nobody had any idea that this abundant life was there on the top of the seamount. That's a deep sea coral right there. And the biologists are completely dumbfounded. They don't know where the energy is coming to feed these things. It might be a deep western boundary current. The Fram Strait is the only deep water exit of deep water passageway in and out of the Arctic. There's a current going south on the east side of Greenland. That's a sponge with a shrimp feeding on it. The shrimp are about 2 centimeters long. And so on the east side of Greenland is the only deep water passageway in and out of the Arctic. That's where all the fresh water dumps out on the surface layer. And there's a deep water countercurrent of salty water that goes to the north. So it may be that deep Atlantic water has got enough nutrients and oxygen to provide for this abundant life at 86 North. But really, we don't know. So this is zooming in with the HD imager. It's got a really nice zoom feature. And this is a shrimp feeding on a dead sponge. When the sponges turn white and get gray hair, that means they're dying or dead. And we sampled some of them, and Beate, the biologist technician for Alfred Wegener Institute, when she curated the samples in the laboratory, she came out, she said, I've been doing this for 20 years. I have never smelled anything as awful as that dead sponge. She says, from here on out, any more samples will be curated by the graduate students. So I want to finish on time. Sorry. So this is taking a push core sample. This is the stinky sample right there. That's it. With the robot arm. And by the way, this is at about 750 meters depth, and we're a couple of kilometers downrange, moving at about 3/4 of a knot away from the vehicle. And this is putting the push core sampler back in the holster. You can see the robot gripper, T-handles on most of the tools. So we had several push cores, a water sampler, and we picked up a lot of biological and geological samples. We're back on the surface here. On this dive, the fiber optic tether stayed intact all the way to the surface. So we were actually having live video from the vehicle as it surfaced. It makes it very easy. It doesn't happen very often. And the weather, we were in this very narrow weather window where a low pressure system was moving, the eye of a low pressure system was moving over us. And there's an interesting story to tell about that because we were just right in between two storms. And that was our last dive of the cruise. I want to finish on time. So acknowledgements, NSF Office of Polar Programs. We developed the vehicle with a NSF MRI grant, and we got matching funds from two private foundations, the James James Foundation and the Jewett Foundation and Woods Hole Oceanographic Institution and Johns Hopkins. I should have put that too, for my part. And the field trials in 2016 were funded by NASA astrobiology program under a Peace Star grant. And 2014 was NOAA Ocean Exploration. And our team is particularly thankful to Antje Boudis, who is now the incoming director of the Alfred Wegener Institute. She's taking over this year. And the officers and crew of the Polarstern for Polarstern Expedition 86 and 101. So thank you for your attention.
Questions for our speaker?
So the polar ice that you're studying, like, what's the salinity like underneath? There must be some interesting mixing going on, and does it affect ballasting?
Yeah, so it depends on the time of year, but there's a low salinity layer right under the ice, which gets deeper in the summer, and then when the ice starts breaking up, then you get a mixed layer, and so you have a low salinity layer with a strong shelf on it. I might actually have a slide here. Let me see if I do. Yeah, so here you go. So this is 700 meters. This is from a CTD cast, and you can see that there's a low salinity layer. This is a salinity in PSUs, and for those of you who are not familiar with this, most of the ocean is typically around 34 or 35 parts per thousand saline in blue water ocean. Most oceans are very stratified with cold, dense water in the bottom, strong stratification, and warm, less dense water at the top. The Arctic is very unusual because it's very weakly stratified, and so things will mix vertically in the Arctic in ways that they won't in other oceans. And you can see the weak stratification here because there's a low salinity layer here going down to about 32 PSU, 32 parts per thousand, which is extremely low salinity. And then by the time we get down to 300 meters, there's almost no change going right down to the bottom. So very weak stratification. I don't have density or potential density plotted here. But you can also see the other thing that is interesting is you can see there's significant mixing in the water column in the first 100 meters. And then the temperature, you have a temperature peak, and it keeps on going down. And of course, the surface temperature is actually below zero, but it can sustain that because of the salinity. And then for the acoustic folks in the audience, in blue water, this is sound velocity here. And in blue water, you'll have a sound velocity minimum somewhere between 200 and 1,000 meters depth. And we have a sound velocity minimum. That means you have a sound channel. And sound that's running down the channel, if it escapes, it'll be directed back into that sound channel. And so it's a deep water sound channel. There's no such minimum here in the Arctic, so it's a very difficult acoustic environment. It's upwardly refracting, and so when you transmit sound horizontally, it heads up, it bounces off the ice, and then bounces again. So it's really the world's worst acoustic channel. And if you do ray tracing, which we do, we get the sound velocity profile, and then we run what's called a bellhop analysis. And so this is for a source that's at 10 meters depth, and you can see what we could figure out here is that we had fairly good coverage we could reach with 10 meters depth along the ice at 10 meters depth. And I have not shown here is that if we put the transducer down at about 80 meters, we've got a good coverage for the first 100 meters. And this bellhop analysis also shows that if we're transmitting here with the transducer at 10 meters and our vehicle's down here, the vehicle won't hear us. Doesn't matter how long we talk or how loud we talk. There's no sound going there. So that's just part of the background work you do when you figure out how to do an emergency recovery. Yes?
Tell us a little more about navigation. Is it like waypoint navigation, or like to find some
So in this,
reference points?
yeah, so we're working on a paper. So in this cruise, we had upward and downward Doppler sonar to measure the velocity with respect to the ice, which is moving, or the seafloor when we're on the seafloor. So we got our best navigation when we're on the seafloor. And the corrections to that navigation came from time of flight measurements with the acoustic modem. I mentioned in my earlier slide that we're combining acoustic telemetry with ranging. And so you know the vehicle's depth, you know the depth of the ship's transducer, you know the exact location of this ship's transducer to within a meter or so. And so every range on the vehicle gives you a circle of location at a certain depth to correct the Doppler dead reckoning solution, essentially. And so we were getting corrections from a modem that's on the depressor, 2 modems on the ship that were about 40 meters apart from each other, and when we deployed 3 subsurface moorings with transponders that were anchored on the seafloor that we surveyed in. So we had 3 fixed beacons on the seafloor, spaced many kilometers apart around the top of the seamount, and then we had 3 transducers attached to the ship, and we could measure ranges from all of those to provide corrections.
How do you estimate the exact longitude of such a transponder that you use?
In this case, it's not so hard because we were only deploying to 600 meters, and they descend at about 60 meters per minute, so the descent rate is really fast. And so in this case, we drop it in, and we know that it's probably within 10 meters of where we put it in. If it's deep water, what we do is we drop it in, and we drive the ship around it, and we range on it. And then it's a simple least squares problem to solve for the transponder position. It's a very straightforward least squares problem.
Let's take 2 more. I think we have time.
Okay, so adding on to that, so what are the actual commands sent by the pilot? Is it positions or is it like velocity and they get feedback from the ship that tells them where they're going?
With tether or without tether?
With
With tether.
tether.
Oh, well, it's either open loop or closed loop control. So your joystick is either commanding an effort, a percentage of thrust where full displacement is full thrust, or if you're in closed loop control, that is commanding reference velocity in that direction. And this vehicle is fully actuated, so it's in principle a holonomic vehicle, but only barely holonomic because our lateral thruster, we have 1 lateral thruster, and the lateral drag on the vehicle is really high. So you can sort of think of it as a non-holonomic vehicle. You'd point up into any current if you wanted to hold station.
How expensive is every expedition that starts in Norway?
Oh, yeah. This one was pretty expensive because we had a total party of 5 engineers and 3 scientists, 45 days, and shipping the gear and things like. So it was close to $1 million. And our 2014 expedition was a little north of $500,000, and that's very inexpensive in comparison to Antarctica, which is where we'd like to go. Antarctica is a lot more expensive by a factor of several.
Yeah, so in your the chlorophyll profile, you had what seemed like something phytoplankton layers.
Yes.
And were they around the isopycnol?
The where did I have that? Hang on a second. Sam Delaney has a paper on this. So what you can see, and I'm not an expert here, I depend on the plankton biologist for this, is that this is chlorophyll and depth. And so everything's pretty much exhausted up in the top couple meters of the water column. And as you might expect, I believe it's because they're starved for nitrate in the upper water column. And so then they migrate down here, and this is 20 meters, and this is about 10 meters. And so there's a big layer of plankton between about 7 meters and about 20 meters. And this is one of those anomalies you get when an organism hits the center of the laser. And so there isn't actually a layer here. This is a transient on the sensor, as are these. There's no layer there.
I'll ask you one question. You have a mission control of about 4 or 5 people running the vehicle?
For this vehicle, it was a full court press. We weren't staffed to do 24-hour operations, and so all 5 of us were on doing the operations.
Would there be value and would there be possibility to increase the autonomy of the vehicle and decrease the number of
absolutely.
mission control people?
Oh, yeah.
What are the prospects? Can you talk about the prospects?
Just time and money.
Is it,
Oh, yeah.
there's no problem that you don't, there's
No, no, no.
fundamental problem.
There's no fundamental problem. But, you know, we were